Hello, welcome back. Today we are doing notes 7C on Newton's laws of motion. So, want you to take a minute to complete the quick review at the top of the page if you haven't done that already. If you haven't done that yet, pause the video, fill that in, and then come back to get these answers. Here we go. All right, so what have we been talking about this whole time? The last set of notes on 7A, Amari. What were we talking about? That was the unit was something over time. What is something over time? Speed. So speed is something over time. How do we calculate speed? What over time? Desiree. Distance. Speed is distance over time. Speed in a direction is, Bryce, velocity. Blank is the rate, and a rate is anything plus a unit of what, Alondra? Time. So we need to know what goes in the blank. Blank is the rate at which velocity changes. People that are absent. People that are absent. People that are absent. Zane. Acceleration. Acceleration is the rate, and a rate is anything plus a unit of time. Acceleration is the rate in which velocity changes. So acceleration can be, promise, changing direction. I'm going to put it on this last line so I have enough room for it. But if you manage to fit it in that first line, it's not wrong. It's just that's the place that I have the most room to fit it. All right, everybody that's in the room has already gone one. So what are the other two examples of acceleration? Speeding up and slowing down. So acceleration is any change in speed or direction. Speeding up, slowing down, or changing direction. Make sure you've got that. Going once, going twice. I'm going to clear it. All right, so again, today we are talking about something that y'all are supposed to already know. It's something that you're supposed to have been given the definitions of in kindergarten, first, second grade. But because I know that a lot of you didn't get that the way you should have or don't remember it or whatever reason, but I've got to build on the concept today. And if you don't already have that base work, can I build a wall on top of nothing? No. Walls built on top of nothing don't stand. So we've got to first go back to the basics. So what is mass? What is mass? Okay, it's a physical property. It's the physical property of what? What does it describe about the object? Weight and mass are different. So your mass stays the same no matter where you are. On the bottom of the ocean or up in an airplane, your mass is the same. On the bottom of the ocean or on the moon, your mass is the same, but your weight is definitely different. So, but you're on the right track. You're thinking the right way. It does have to do with something about the object's size, but not the space it takes up. So what's the other way that we can think about an object besides the space that it takes up? We can think about how heavy it is, right? If I have a tiny little object that's super heavy, it's got a lot of mass, even though it's tiny. And if I've got a big inflated balloon, it's huge, but it doesn't weigh nothing. Because does it have much mass in it? No, it's mostly air. So what is that word to describe that? It starts with an M too. And it's that word that you're supposed to learn in kindergarten. Solids and liquids and gases are all matter. Solids have more matter in them because the particles are packed closely together. Liquids have a little less because the particles are loosely flowing. And gases, the matter's flying all over the place, right? Matter. So what is mass? The amount of matter in an object. Okay, we just talked about the fact that your mass stays the same no matter where you go, but the weight changes. So, what is weight then? Okay, all right, well, think about what I told you about weight, the weight differences, that your mass is the same on Earth and on the moon, but your weight is different. So, then what's the difference between on Earth and the moon? What are the two things that are different there? The amount of gravity, right? So, then what's weight? Your mass affected by gravity. Your weight is how much is gravity pushing down on your mass. Okay, so weight is mass affected by gravity. So to get an object's weight, you take its mass and you multiply it by the gravity at the place where it's at. And so that's why you can weigh differently depending on where you're at. So your mass remains the same no matter where you are. If you're on the ocean floor, if you're at sea level, if you're on top of a mountain, if you're on an airplane, or if you're in space, your mass stays the same. However, your weight would change. And we just pointed out why. Why? Gravity, because gravity is different in all those places. All right, going once, going twice. All right, so we're going to have a little story time here. I'm going to introduce you to my buddy Isaac Newton. This dude, all right, first of all, I need you to put yourself in his shoes, and I think you can. Number one, he was ridiculously smart, but was not rich. Yes, he was the right color for his time. Now, why do I say that? Okay, 1643 to 1727. He was the right color and he was the right gender, but he didn't have enough money. So, did black folks go to college back then? No. Did women go to college back then? No. Did poor white men go to college back then? No. Now, he was a poor white man. His parents were tenant farmers. So, they had a house, but they didn't own it. They worked land, but it wasn't their land. So they were relatively poor. It would appear that they were rich because they looked like they had a land in the state, but it didn't belong to them. They had to pay tax, rent, and all that stuff. With me so far? All right. He was really, really smart. And I can't remember. I probably should look it up. Did he go to Cambridge or Oxford? Cambridge. All right. So Cambridge. He went to Cambridge, and while he was there, and this is the other thing you're going to identify with, the Black Plague came through, and everybody got sent home. Does that sound familiar? Yeah. So now I need you to go back a little bit. He did get to go to Cambridge, but he was poor. So do you think he just got to just go to Cambridge? No. So he did kind of a work study thing. Now these days, everybody work studies. And it is totally common for your bestie to be serving your lunch to you and give him a fist bump and say, I'll see you later. And it's totally fine and nobody thinks anything of it. So that's the first thing is for you to understand is scholarship kids weren't really a thing and especially weren't accepted. Now, do you think that they went through a lunch line with a tray and served themselves and then sat down and ate and then bust their own tables back then at a rich white men's school? No. So when he was serving them food, it was, yes, sir. No, sir. And then had to sit next to the person that he had just been treated like dirt by in class. Can you imagine? It's my buddy Isaac, right? Exactly. Yes, I can. My buddy Isaac, man, he went through a lot. And then he got sent home. Now, because he had been in the big city at college and possibly exposed to the Black Plague, when he came home, even though he wasn't sick, they put him in, say it with me, quarantine, right? In the attic. Oh. And they brought him meals and stuff, but he was stuck in the attic. He got bored and wrote a book called Principia. Basically, he invented calculus. Smart dude. Now, while he was going through this time of just sitting around out there at the farm, at some point he was in the orchard and something happened that you have seen over and over and over again. What is he credited with? What happened? Discovering gravity. Why? Because an apple. And they always show it hitting his head. Don't know if it really did hit his head, but supposedly an apple fell from the tree and he went, what is it that made the apple fall? And he figured out gravity. So Sir Isaac Newton was an English physicist and mathematician and is credited with establishing laws that explain the principles of modern physics. So how objects move and are affected by the world we live in. He's the what guy? What's that piece of fruit? Apple. Yeah, he's associated with the apple. He's the apple guy. Isaac Newton and watching the apple fall. All right, so Newton's laws of motion. There are 3 of them, and we have to know them all. Going once, going twice. All right. Newton's first law of motion. I call it the school bus law. Due to inertia. Say that with me. Inertia. You say it? Inertia. Inertia is an object's tendency to resist motion. Okay, well, what does that mean? Objects in motion tend to stay in motion. Objects at rest tend to stay at rest unless acted upon by an unbalanced force. An object in motion tends to stay in motion. An object at rest tends to stay at rest unless acted upon by an unbalanced force. This ball is just sitting there at rest, and it will tend to stay at rest unless I do what? Act upon it with an unbalanced force, a push or a pull. So if I kick it, that's an unbalanced force. That makes it move, and it's not going to stop until all of that force is expended or it hits another object. So why do I call this the school bus law? This is the school bus. This is you. This is the school bus. This is you. And I don't know where I'm going to have to be. I guess. Can this be seen? Yes. Okay. All right. So, school bus, you. You're riding along in the school bus. School bus stops. What happens to you? Right. You keep going. So, this is why the backs of bus seats are tall. Because kids don't pay attention. And when the bus stops, you're going to knock heads with the person in front of you if those seats weren't so tall. So those big, tall seats make it so that you knock heads with the seat or can put your hands out and brace on the seat. What about when the bus is stopped, right? So the bus is stopped and you picked up somebody and then the bus starts again. What happens to you? Right? And think about a plane launching or a F1 car taking off. What happens? Right? Because you're still and want to stay still, but then get pushed back in your seat. All right, so let's put that into our own words. A moving object keeps moving unless what do I write? A moving object keeps moving unless But why would it get okay? So let's put that. But acted upon by an unbalanced force is what it says. So let's put it into our own words. Unless something stops it, hits it, sure. All right, that's the first half of it. What about an object at rest tends to stay at rest? So an object will stay still unless something, right, unless something makes it move, unless something pushes it. When you are riding the bus and it stops suddenly, what happens to you? We just said it. You hit the seat in front of you. That is because of Newton's first law of motion. You and the bus were traveling at 35, 45, whatever it is, miles per hour. And when the bus applied the brakes, it stopped, but you didn't. So we've already seen the demonstration. We'll show you one more time. What happens? Cup stops. What happens? Right. Cup stops. Ball keeps going. Put that in your own words. You can just write cup stops. Ball keeps going. Going once, going twice. So how does this illustrate Newton's first law of motion? How does our school bus thing illustrate it? What's the definition of Newton's first law? Okay. What happened in the demonstration?
The school bus stopped.
So how can we put these two together? First law is an object in motion stays in motion unless it's acted upon by an unbalanced force. Object at rest tends to stay at rest unless acted upon by an unbalanced force. And then you told me that on the bus, I'm tootling along, and when the bus stops, I keep going. How is this an example of Newton's first law? Put the two together. It's a perfect example of Newton's first law. How? What is it that's happening either in the cup and ball demonstration or on the school bus that is an example of Newton's first law? What is it that's happening that is like, yep, that's Newton's first law? Okay, so we've got you on the bus and you want to stay in motion. So even though the bus stops, what happens to you? You keep going. All right, the second half of that is that all of these examples are of an object that is moving. What about objects at rest? So what makes an object at rest, like the ball sitting on the floor, stop being at rest? Okay. A force, right. Somebody pushes it, pulls it, wind blows it, something. So a force. So we get some sort of push or pull. So that would be an example of an unbalanced force. Now, why doesn't the ball roll on forever? Like if I was to move that table out of the way and kick the ball, would it go forever?
No.
Why not? It's going to hit something, right? It's going to hit the wall. It's going to hit boxes, a table. It's going to hit something. So there's your unbalanced force that makes it stop again. What if I had an infinite, endless hallway? Okay, so eventually friction would slow it. There's another force that's unbalanced. So friction is the unbalanced force pulling on the bottom of it. And there's another unbalanced force that's pushing gravity. So, but those two unbalanced forces will eventually stop the ball. Now, what about in space, where there's no friction and no gravity? It will keep going until it either hit an asteroid or got pulled in the gravitational field of something else, got sucked into a black hole, whatever. It's going to keep on going forever because there's no friction, there's no gravity, there's no unbalanced force to make it stop. All right, so why doesn't the ball roll on forever? So we've got two unbalanced forces that are pulling on it or pushing on it. What are they? Friction and gravity. And then it also could just hit something. All right, Newton's second law of motion. The way I remember this one, the bigger they are, the harder they fall. You have all seen those videos, memes, whatever you want to call them, where two people have those exercise balls and they run at each other. Now, when they're about the same size, they just, and ha, 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 ha. But what happens when one of them is significantly smaller than the other one? Which one goes, bing? The little one, right? The big person's like, whoo. And the little guy goes, boom, and goes flying. Why? Because of Newton's second law. Force equals mass times acceleration. The bigger something is and the faster it's moving, the more force it has. That makes sense, right? Now, bullets are tiny, but they go fast. So even something very small, if the acceleration is fast enough, it can still have a lot of force. So, force equals mass times acceleration. The bigger something is, faster it's moving, the more force it has. All right. You're driving down the road, cruising at 70 on the interstate. And you come up and there are two vehicles. They're blocking both lanes. You try to hit the brakes, but your business partner has cut the brakes, trying to get you out of the business and collect on the life insurance policy they took out on you. Tisk, tisk. You can't go off the road. One side, you got to drop off into a lake. The other side, you got to drop off into woods. You will not survive. So you have to hit one of the vehicles. You've got a 25-ton, 18-wheel tractor trailer and a 1-ton sedan. Who are you going to hit?
The sedan.
Why?
Because it's smaller.
Yes, it has less force. That tractor trailer has way more force than you want to deal with. So aim for the sedan. Going once, going twice. If you're watching the video, you know by now to pause it if you need to, right? Right? Yeah. I swear when I do that, I feel like Dora the Explorer. All right. Newton's second law. Newton's second law of motion states that the force applied by an object equals its mass, which is defined as the amount of what? That other M word? Matter. Times its acceleration. And we know that acceleration is the object's rate of change in, the distance over time is speed. Speed in a direction is velocity. The rate of change in velocity is acceleration. So now that we've worked it backwards, let's fill it in. Acceleration, which we know is defined as an object's rate of change in velocity. And we know that velocity is speed in a direction. Ooh, all right. We will be having a test on this when we get back from Thanksgiving break, so please study. Anyway, let's simplify it. Force equals mass times acceleration, or F equals M times A. We're putting that into our own words. Force equals mass times acceleration. So what does that mean? What does that mean in your own words? Force equals mass times acceleration. Okay, but in your own words, so what does that mean? What is mass? What will it be like if it's massive? If it has a lot of mass, what's it going to be like? Heavy. Yay, we're getting somewhere. So the heavier something is, what's the next part of it? And the faster it's moving, the more, let's not use force because that's the word. So the more sure, the more strength it has. Going once, going twice. Newton's third law of motion is the bouncy ball law. Newton's third law of motion states that for every action, there is an equal and opposite reaction. That was pretty straightforward. For every action, there is an equal and opposite reaction. Why did that happen? I put all that force into it and then didn't tie it up. So when I let it go, all that force was released. And what did the balloon do? Well, it just didn't fall. Right, it flew all around. It used the propulsion, that action reaction. So, how can we put it in our own words? For every action, there is an equal and opposite reaction. Okay, so putting more force into something will make it go further. So when I swing hard at that baseball that's coming at me at 90 miles an hour and I smack it perfectly and the ball now goes away at 60 miles an hour, that is action, reaction. For every action, there is an equal and opposite reaction. NBA star jumps off the boards, which push up, and he makes a slam dunk. What are basketball gym floors made out of? Wood. And which direction are the planks oriented? This way or this way? Right, long ways. Were any of you lucky enough to have somebody set up a board on bricks for you when you were a little kid? You should have them do it now because it's not too late. So you get 2 cinder blocks, 2 bricks, you put a little, put board on it. First you got your balance beam, but then when you get to the middle, what happens? Right, now you got a trampoline. Yeah, it's springy in the middle. Wood is especially springy, so when you push down into it, it gives you that energy back when you jump. So that's why we want to make our basketball gym floors out of it. Do we want our floor made out of concrete? What happens to all the energy then? Yeah, it gets sucked in. The concrete absorbs the energy rather than giving it back. All right, so a bouncy ball hits the floor and, bounces back up. Now, because of gravity, it doesn't bounce as far as it, I'm going to drop it from here and it's not going to make it back up because of gravity, but it does bounce back up. You come up with your own. You could use the one that I just used to introduce the law. All right, quick review to sum it all up. I'm going to wrap it up. So we have Newton's first law. The short definition is inertia. What is inertia? An object's resistance to change in motion. Inertia is a property of matter. As you are exiting or entering onto, let's say 288 off of 360, what happens to everybody in the car? Why? Because you're turning. Inertia. Your body wants to keep going straight, but the car is turning. We call those COD turns in my, come over, darling. Because you end up leaning in. You hope you're friends with the person you're sitting next to. Silly way to remember it is the school bus law. And you draw anything that you think will help you remember it. I'm going to draw a ball with a foot coming in to kick it. Newton's second law. The short definition is actually the law. It's just the formula that is the law. F equals m times a. What's F stand for? Force. What's m stand for? Mass. What's a stand for? Acceleration. Force equals mass times acceleration. Silly way to remember it. The bigger they are, the harder they fall. The other way to remember it, if you'd rather write it, is the if you think you remember it easier, is the exercise ball. Like if you want an exercise ball, if that's a better way for you to remember it, that's fine. So either the bigger they are, the harder they fall, or exercise ball. Because you remember that when two people smack into each other and one of them's a lot bigger. Oh, I forgot to show y'all this. Again, I don't know if the folks at home are going to be able to see it. Be able to see this? Maybe. I'll move the water bottle out of the way. Maybe if I do it right here. All right, so I've got two rocks here. Confirm for me. I mean, we can tell that one's bigger than the other, but confirm that one is significantly heavier. Okay, second opinion. Is it significantly heavier? Is it significantly heavier? All right, we have three people agreeing that the larger rock is significantly heavier than the smaller one. All right, so I've got my target here, and I'm going to, now I'm not a robot, so I can't be perfect, but I'm going to try to throw them at each other at the same speed so that they hit right there in the middle. Now, thinking about what happens with the exercise balls, what should happen? The small rock should go flying. Let's see if it happens. There's one proof that it worked. Let's try it again. That one wasn't as good. Let's see. So, the larger rock stays like exactly where the two hit, but the little rock goes flying. Sometimes more than others, but the little rock is always the one that moves. All right, so picture for this one. What's that mean? What's that supposed to illustrate? He's in trouble. All right, third law. Action, reaction is the short definition. Silly way to remember, balloon. And oh, I guess I don't want to do that though, do I? Let's move it over there. A rocket taking off? It works. All right. Make sure you have all that. Have a lovely day and make good decisions. Bye.